Good evening, everybody, and we are ready for roundtable 15 with Realistically Speaking, and the topic today is measuring distance via parallax. So, realistically speaking, are you there?
I'm here.
Hi, nice to see you. Nice to see you. So, do you want to tell us quickly just about your presentation, and then we'll get straight into it?
Sure. So my presentation is going to be about using parallax as a method for determining distance between an observer and an object. I'm going to go through a bit of the math behind it. I'm going to use a real-world example of something I did just this morning. Then I'm going to apply the same technique to the moon to attempt to determine the distance to the moon. And then I have some extra material that I tacked on at the end after I watched your recent episode with Sleeping Warrior. So he mentioned stellar parallax, so I've included a little appendix about stellar parallax.
Okie dokie, well I can't wait to see what you've got, so without further ado, I'll put you on full screen, and away you go.
Alright, thank you, Ranty. So I'm Jeff. My YouTube channel is Realistically Speaking. I don't tend to put a lot of content out. But this is my offering for the roundtable discussion. So I want to start by saying, how do we perceive movement? We can perceive movement in generally two ways. One of them is the change in the apparent size of an object. So let me replay this slide. You're going to see this object appear to grow in size. And that would seem to indicate that the object was moving toward us because it was getting bigger. Or at least it appeared to be getting bigger. Another way that we can perceive movement is by change in an object's apparent position. So this object appears to be moving from right to left, and so we perceive it to be moving. How can we perceive an object's apparent size? We can describe or define it as saying it's the amount of space taken up by an object in our vision. We can use slightly more mathematical terms, and we can say instead that the apparent size of an object is the angle subtended by the object in our field of view. And what that basically means is if you were able to measure the angular space that an object takes up in your field of view, that can tell you its apparent size. We tend to use angular size and apparent size interchangeably. Now for a quick example of how the change in apparent size works. It's a relatively simple relationship. When an object increases in angular size, meaning it appears to be bigger, as its distance from the observer decreases. So as the object is getting closer to you, it increases in angular size. An object decreases in angular size as its distance from the observer increases. So the further away an object gets, the smaller its angular size. And this short animation here shows an object. It's a ball of radius 1, and it is 5 units away from the observer. And at the beginning, it has an angular or apparent size of 23.1 degrees. And you'll see as it moves further away, its angular size decreases. The actual size of the object stays the same, but the angular size, the amount of space of your vision it takes up, decreases as it gets further away. How do we perceive apparent position? Again, we can define or describe it as the location at which an object appears. And again, we can use slightly more mathematical language, and we can say that the apparent position of an object is the angle relative from a point of reference to the point at which the object appears. So for example, if you're looking straight ahead of you and you need to turn your head 10 degrees to see a light switch, we can say that the apparent position of that light switch is 10 degrees away from the reference point, which is directly in front of you. How does a change in apparent position work? If you have two objects of the same size at different distances, but they're moving at the same rate, then the closer object will appear to be changing its position faster, and the farther object will appear to be changing its position more slowly. And again, I have a simple animation which shows this. These two circles are the same size. They're radius of 1. One of them is 6 units away from the observer, and the other is 12 units away from the observer. The observer is here, and he's looking straight ahead, which for him is to our right. The closer object appears to be 33.7 degrees deflected from looking straight ahead, and the more distant object appears to be 18.4 degrees. These two objects are now going to cover the same distance, 1, 2, 3, 4 units of space, in the same amount of time. But the closer object is going to appear to the observer to be moving faster than the further object, because the closer object is going to cover a greater angular distance in the same amount of time. And you can see here, even though the two objects are moving actually at the same rate, the closer object will appear to the observer to be moving faster because it is appearing to change its location faster. It has to cover more than 33 degrees of visual space in the time that the more distant object has to cover only about 18 degrees. Now that we have these concepts of apparent size or angular size and apparent position or angular position, now that we have those concepts behind us, now let's talk about parallax for real. Parallax is the change in the apparent position, not the actual position, the change in the apparent position of an object when observed from two different lines of sight. You can quickly do an example of parallax on your own. Simply hold out your hand in front of you and stick your thumb up and close one eye. Your thumb will look to be in a particular location against whatever the background of the room you're in. When you close the open eye and open the closed eye, your thumb will appear to jump or shift position slightly against the background. That's parallax in effect. This diagram here shows it as well. We have two observers, one at point A and one at point B. Observer A looks at this object, this yellow star, and for viewer A, it appears to be in front of this blue background. For observer B looking at the star appears to be in front of the red background. This apparent shift in location can be measured as an angle. The angle between these two observers and the object itself is actually twice the angle of parallax. Parallax is defined as half of this angle. So parallax is measured as the angle between two lines of sight. And using that angle, we can determine the distance of the object we're looking at. If we know the distance between our two observers, we can establish a baseline. And if we can measure the angular shift of the object, then we have a triangle. We have a baseline and an angle opposite the baseline. And using some simple trigonometry, we can use the tangent function to determine the length of the distance. In this half of the triangle, half of the baseline, the distance, and this part of the angle, we can use the tangent function. Tangent of this angle is this distance over this distance, or this side over that side. So if you look at these equations here, the tangent of this entire angle divided by 2 is equal to this half of the baseline divided by this distance. Moving things around, we can say that this distance is equal to half of this baseline divided by the tangent of half of this angle. I'm going to be following these steps in a few moments using actual real-world example. But first I want to tell you what parallax depends on and what it doesn't depend on, because this is a somewhat contentious issue. Parallax requires you to have some object, some target that you're attempting to determine the distance to. It also requires you to have a more distant background behind that object. You need to know the distance between your two observers, and if the object is believed to be moving, then these two observations have to happen simultaneously so that both observers are seeing the object at the exact same location in real space. And finally, the object should have the same apparent size in both observations. What this tends to mean is that the two observers should try to be the same distance from the object they're looking at. And a way that you can approximate this is by saying, does the object appear to be the same size to both observers? If so, then the two observers are probably about the same distance from the object. What doesn't parallax depend on? Parallax does not depend on the mass or the density or the volume or the makeup of the object you're looking at. It doesn't depend on the speed of the object because parallax measurements of the sort I'm describing are taken at the same time, instantaneous. It doesn't matter what the object is. It could be a projection on a screen for all we know. And it doesn't depend on the surface from which the observations are being made. In other words, parallax measurements do not assume the shape of the Earth. They do not start by assuming a radius, and they do not start by assuming the Earth is flat. How can you improve the accuracy of your parallax measurements? Well, you can make sure that the background is as far away behind the object as possible. The farther the background is behind the object, the more accurate your measurement will be. You can increase the distance between your two observers. The larger the baseline, the larger the angle you will measure. And it's easier to measure a large angle than a tiny angle. And finally, the smaller the field of view. In other words, if you do have to be measuring a small angle, it's important to have as much precision, as much granularity on that angle as possible. There is a big difference between 0.1 and 0.2 degrees. If the actual angle you're measuring turns out to be 0.16 degrees, rounding that up to 0.2 can make a big difference in your parallax measurement. So having a smaller field of view allows you to measure the angle more precisely. So here's a simple flow chart or step-by-step. How can you measure the angle of parallax? First, you need to establish a known angular reference. Then you need to determine the pixel to angle ratio of the images you're using. You overlay the two images that you take so that the background lines up, and you'll notice that your target object is in slightly different positions when you line up the background. You then measure the pixel offset of the object between those two images. You can then convert that pixel distance to an angle by using the pixel to angle ratio. And that change in position described as an angle is the angle of parallax, or in our case, it's going to be twice the angle of parallax. So I'm now going to follow the actual steps with an observation I made just this morning on the top of a parking garage in New Brunswick, New Jersey. First thing I do is I establish a known angular reference. I'm going to place an object whose size I actually know at a distance I know, and I'm going to compute its angular size. There's a simple function for this. I'm sure you've heard Red's rhetoric mention this formula a number of times. The angular size of an object, if you know its width and its distance, is 2 times the arctangent of half the width divided by the distance. So this is a whiteboard that I have in my basement above a chest freezer. It is about 23 inches wide. I'm going to stand at the foot of my basement stairs, which are about 80 inches from the object, and I take a picture. The angular size of my 23-inch whiteboard from 80 inches away is 16.36 degrees. And I can verify this with GeoGebra by creating a line 23 inches long, or 23 units long, 80 units away from my observer, and measuring the angle from A to C to B. And the angular size rounded to a single decimal place is 16.4, which is what you get when you round 16.36 up. So I've successfully determined the angular size of a 23-inch object from 80 inches away should be 16.36 degrees. I'm now going to determine the pixel to angle ratio of my camera. I'm going to take the width of the object in pixels and divide it by the angular size. So opening up the image I took in Paint, the horizontal width in pixels of the whiteboard turned out to be about 1,012 pixels. I divide 1012 pixels by 16.36 degrees, and I get that the angular resolution, not the angular resolution, but the pixel to angle ratio of my camera is about 61.86 pixels to 1 degree. I'm going to need this ratio later when I take my next pictures. So I went up to the top of a parking garage in New Brunswick, New Jersey, and I took 2 images separated by about 4 inches of this red metal post. You can see it in both images here. These are 2 different images. You can tell I have my finger partially obscuring the image here. You can also tell they're different images because this green section of the wall is in a different location relative to this concrete than it is over here. So you can tell for sure that these are 2 different images. And now what I'm going to do is overlay them so that the most distant background overlaps. This is just to establish this is the surface I took the image from. I took it in line with this yellow paint right here. And I had my camera, I had the eyepiece placed at the 6 and the 2. So the images were taken about 4 inches apart. When I overlay the 2 images, make one of them transparent so I can see both of them at the same time, and then I line up the trees so that the trees in the background match, I can see that my target is in slightly different locations. I then zoom in and measure the number of pixels that the object appears to have moved. And in this case, it appears to have moved to the side by 17 pixels. So that's the pixel offset. I now take the pixel offset and divide it by my pixel to angle ratio. 17 pixels divided by 61.86 pixels per degree gives me an angular shift of 0.275 degrees. Now, using my known baseline of 4 inches and my known angle of 0.275 degrees, I can determine the distance to that object. If you follow along the math here, you come out with a value of 833.4 inches. Now, I have the advantage of being able to verify this distance. Again, this is the location I did it from. This is the top of the parking garage. You can see that this is New Brunswick, New Jersey. There is a luxury apartment complex called the Quincy right here. That's who this parking deck belongs to. There's Nielsen Street right here and some other businesses. So if anybody is in the New Brunswick, New Jersey area and wants to validate or test this for themselves, they can go to the exact same place that I did. I was standing right about here, and the object I was photographing was right there. You might be able to see these faint yellow lines. These are parking space dividers. From where I was standing at this red dot to where the object was at this red dot, there were 1, 2, 3, 4, 5, 6, 7, 8 complete parking spaces, and then a little bit extra. I measured 1 parking space to get an estimated width of every parking space. So it looks like each parking space is about 97 inches wide. Then I went to the edge of the last full parking space and measured the distance from the object to the edge of that parking space, and I got a distance of 67 inches. So doing the math, 8 parking spaces, assuming they're all 97 inches, gives me 776 inches. The remaining was 67 inches. Add these 2 numbers together, you get 843 inches. That's my approximation using a tape measure of how far away the object was from me. Compared with my computed parallax distance of 833.4 inches, I was off by less than 10 inches, which is within 1.2%. That's a really good degree of accuracy. Now, I could refine these numbers by measuring the actual distance, not assuming all of the parking spaces are 97 inches. And I could also make my parallax measurement more accurate by making exactly sure that the distance was 4 inches between one image and the other, instead of maybe 3.8 or 4.2 inches. Making sure that I have the exact length of the baseline would improve my accuracy. We're going to follow the exact same steps we just followed, but this time our target is going to be the moon. For my baseline, I've chosen the distance between Trenton, New Jersey and Miami, Florida. Google tells me this distance is about 1,046.5 miles. I'm going to assume that distance is accurate. If that distance is inaccurate, I will gladly accept corrections and I will plug that number into my equation and we can get a slightly better estimate to the distance to the moon. Because I can't be in Miami, Florida and Trenton, New Jersey at the same time, I'm using the free planetarium software Stellarium to take 2 simultaneous images of the night sky from those 2 locations. On the left, we have Trenton, New Jersey, and on the right, we have Miami, Florida. Both of these images were taken at the stroke of midnight on December 12th of this year. You can see that the field of view of both of these images is 13.4 degrees, and that refers to the field of view from top to bottom. And you may be able to detect with your naked eye that the moon appears to be slightly further away from this star in the left-hand image than it does in the right-hand image. The image is 1,080 pixels tall, and Stellarium tells me that my field of view is 13.4 degrees. And that means that these 2 images have a pixel to angle ratio of 80.6 pixels per degree. When I overlay the 2 images, the stars line up, but the moon doesn't. When I measure the pixel offset of the moon, I create this rectangular box. The box is 20 pixels by 6 pixels. Using the a squared plus b squared equals c squared, I can measure the distance of the diagonal, and that comes out to about 20.88 pixels. Dividing 20.88 pixels by our ratio of 80.6 pixels per degree, I get an angular shift in the moon of about 0.26 degrees. And since the moon is about half a degree in angular size, you can actually see that that checks out. This appears to be about half the height of the moon. And if the moon is about 0.5 or 0.52 degrees, then it really has appeared to move about half of its own width. So again, our angle here is 0.26 degrees. Now we do the math. Our baseline was 1,046.59 miles. We divide it by 2 times the tangent of the angle divided by 2. That comes out to 230,526 miles. Let's compare that to what Stellarium says the distance to the moon was. Stellarium gives me the distance in kilometers, which I can convert to miles. And when I compare 233,978 to my computed value of 230,526 miles, I'm again within less than 2% off. I'm within 1.5%. And if the Earth happens to be spherical, then this distance could be made up somewhat by adding the distance to the center of the Earth and adding the distance to the center of the moon. Now, I can hear some objections, so let me address some of them. How can we be sure that the stars are farther away than the moon? In other words, how do we know that the stars are a legitimate background to use? The moon, even its non-illuminated portion, can block the stars from view. The moon can block the stars from view, which means the moon is in front of the stars, or at least that's what the evidence suggests. How can we be sure that the stars are very far away? The fact that they exhibit no easily detectable parallax, Anthony, I'm looking at you, from any 2 locations on Earth, indicates that the stars are so far away. The fact that the moon does demonstrate detectable parallax makes it sound like the moon must be closer than the stars. And finally, how can we be sure that the moon is real? That is an irrelevant question to parallax. Let's assume the moon were not real. Let's assume instead the moon were a projection. That doesn't change the fact that there is some source of light 240,000 miles from Earth. However, the features of the moon, for example, the craters that we can see through a telescope, and the opacity of the moon the fact that the moon obscures things behind it, even the non-illuminated portion of the moon does this. That is evidence that the moon is real and physical. This was going to be the last slide of my presentation until I saw Sleeping Warrior's comments about stellar parallax. But I'm going to present this now and then move on to my bonus material. Why does lunar parallax matter? Why does it matter that parallax, a technique for measuring distance that doesn't depend on the shape of the surface the observations are made from, consistently and repeatedly measures the moon to be over 200,000 miles away? Generally, you will measure it to be between 220,000 and 250,000 miles away. Why does this matter? Why is it significant? It means that the moon is nearly 250,000 miles from Earth. It also means that the moon is approximately 2,160 miles in diameter. And how can we come up with that number? We know its angular size and we know its actual distance, and that means we can know its actual size. These two things combined mean that moonrise and moonset, as seen from Earth, cannot be explained merely as effects of perspective without requiring severe amounts of refraction of light. Severe refraction. If you were to model this out on a flat Earth and have the moon being 250,000 miles away, the moon would almost always appear more than 85 degrees above the horizon. In order to get the moon to appear anywhere near the horizon, you would either need to be millions of miles away from it, or there would need to be excessive refraction of light. Refraction of light to the point that one could not even be sure of simple terrestrial distances. This is evidence against a flat Earth and in favor of a spherical Earth. But wait, there's more. Sleeping Warrior said that Sirius is one of the closest stars, whereas Betelgeuse is something like 464 light years away. There has to be stellar parallax. There is stellar parallax, Anthony. It's just really, really tiny. The Earth is about 93 million miles from the Sun. We call this distance 1 astronomical unit. Earth-based parallax of stars uses a baseline of 2 astronomical units. We look at where a star is one day, and then 6 months later, when we're on the other side of the Sun, we look at the star again. This gives us the baseline for the triangle that we create. In terms of distance, there are over 63,000 astronomical units in a light year. Sirius is about 8.6 light years away from Earth. The parallax angle for a star 8.6 light years from the Sun is 0.0379 arc seconds. 1 arc second is 1/3600th of a degree. So the parallax for Sirius is about 1/3 of an arc second. Betelgeuse, which is about 642 light years away, its parallax is 0.00508 arc seconds. Even though Sirius's parallax is about 76 times Betelgeuse's, they're both minuscule, and that degree of movement is beyond the human eye's capability of resolving. You need to use very powerful telescopes in order to detect this movement. To give you a terrestrial example, let's imagine that you are looking at 2 objects that appear to be along similar lines of sight. In other words, you're looking at them, and from where you're standing, they appear to be next to each other. One of them is 8.6 miles away. The other is actually 642.5 miles away. Now you move your head 1 inch to the left. Does A appear to have changed its position relative to B? That distance of moving your head 1 inch for something that's 8.5 miles away and 642.5 miles away, that is the exact same scale as moving your head 1 astronomical unit and expecting to see a shift in objects 8.6 light years away and 642.5 light years away. We can try to measure this using the closest star other than the Sun to Earth, Proxima Centauri, 4.22 light years away. These are two images from Stellarium. The location doesn't change, but one is 6 months later than the other. Oh, actually, one is only 5 months later than the other. My mistake. The field of view of those two images was 0.206 degrees. Stellarium reports that the parallax for this star is 0.77233 arc seconds. These are the two images overlaid, and you can just barely see that the star is in a slightly different position. These two stars lined up the same. This star appeared slightly shifted. This is that image zoomed in. This red pixel moved to there. The pixel to angle ratio of the images, 1080 pixels divided by 0.206, gives me a ratio of 5,242.71845 pixels per degree. The object shifted the square root of 5 pixels, which is about 2.236. Dividing the pixels by the ratio gives me an angular shift of 0.0004265 degrees. Turning those degrees into arc seconds, we get 1.535 seconds of arc. We take half of this angle because the parallax angle that we use for space is half of the angle you measure. So it comes out to 0.767 arc seconds. So that's the parallax I measure by doing my comparison of the two images. If I just attempt to compute the parallax mathematically, I take the inverse tangent of 1 astronomical unit divided by 4.22 light years, and I get 0.000214694 degrees. Turning that into arc seconds, I get 0.7728989 arc seconds. Comparing my two numbers, I'm within 1%. And looking at the reported value from Stellarium, I'm incredibly close to this. And as it turns out, my numbers were slightly wrong here because I only did 5 months difference and not 6 months difference. If I added another month in between those two images, this number would be higher and closer to that. That's the end of my presentation. So now I will gladly listen to any commentary or questions from the audience.
Okay, well, thank you very much. Thank you very much. Right, I am sure we're going to have a few questions. I can see there has been some chat going off. Let's just wait and see if we get any questions through. So it's probably going to take a little while because we are working on a time delay. So we're around about 40 seconds in front of the chat. So fingers crossed we'll get some questions for you soon. Maybe you could answer one of my questions. How long have you been on researching flat Earth?
I found out about flat Earth YouTube videos when I was preparing to drive down to South Carolina in August of 2017 to view the total solar eclipse. A couple months before that, I was studying up, like, what should I expect to see when I see a total solar eclipse? What should I be doing? What should I be paying attention to? And I found a video that said total solar eclipses were hoaxes. They were moving in the wrong direction. And that was what led me to find an awful lot of flat Earth content on YouTube. And I suppose my story is somewhat different to many others because I listened to the flat Earth claims about the shape of the Earth. I tested their claims, and their claims didn't hold water. And when I tested the claims of the spherical Earth, those claims did hold water. So I'm not one of those people that stumbled upon flat Earth, tried to disprove it, and failed and became a flat earther. I'm still utterly convinced that the Earth is spherical.
Okay, well, currently we only have one question right now. Now, I know Sleeping Warrior did want to post a question, but already I've forgotten it because he did it right at the start of the presentation. So there is a question up. Pretty ludicrous question, but maybe you want to answer it. How long is your tape measure?
The tape measure measures at least It measured at least 8 feet, um, because the parking spaces were 97 inches wide. So the tape measure can measure at least 8 feet. I have a feeling it can probably measure up to like 20. It's in my car right now, so I can't confirm that. I'm pretty sure it's a 20-foot tape measure.
So, from flat enough, explain a Selenhelion eclipse.
Okay, I will describe a Selenelian eclipse, even though it's completely off the topic of my video. So a Selenelian eclipse is when both the sun and the moon appear above the horizon, and yet the moon is in an eclipse. The flat Earth reasoning behind this would be that it's impossible for this to occur on a spherical Earth because the Earth has to be in between the sun and the moon in order to cause that shadow. There are two rebuttals to that. First of all, it's well known that the closer an object is to the horizon, there is greater refraction of light on that object, which is why you will hear pretty much any person who understands spherical science, like, astronomical spherical science, they'll tell you that when the sun appears to be on the horizon, its actual location is almost about a half a degree below where it appears to be. And that's because as the light of the sun enters the atmosphere, it bends slightly because of the steep angle that it's coming through the atmosphere at. And the same would go for the moon. That's one rebuttal. The second rebuttal is that from even 1 mile elevated above the Earth, you can still see this effect even if refraction weren't the case. If you were on a spherical Earth, 3,959 miles in radius, and you were at an elevation of 1 mile above sea level, and it were the exact moment of sunrise and moonset, you could still see a Selenelian eclipse without even taking refraction into effect. And you can prove this, you can demonstrate this yourself by opening up a program like GeoGebra and putting in the sizes and distances of the sun, the moon, and the Earth, and making your observer 1 mile above the surface of the Earth. And that observer would be able to see the sun above his horizon, he'd be able to see the moon above his horizon, and yet the light from the sun hitting the Earth would be casting a shadow on the moon. So that's my description and my explanation of how a Selenelian eclipse is possible on a spherical Earth.
Okay, well, in the meantime, we have had lots of questions. So, do you agree that the orbit of Earth is an assumption?
I don't agree that the orbit of the Earth is an assumption.
Okay, so a question from Dilly Gill. What is your source for these measurements? NASA? ? If NASA were to change the distances tomorrow, would you go along with it?
I did not employ NASA at all. If that person had watched my video, never once did I require NASA to provide any distance for me. The only distance that I measured in this entire video, or the only distance that I used in this entire video that I didn't measure myself, was the distance from Trenton to Miami, and I had to take Google's word for it. When I did my example on the parking garage, I measured those distances myself. You can prove that parallax works for terrestrial measurements, and you need to explain why it wouldn't work for a celestial measurement. So again, I didn't rely on NASA for any of my numbers, and if NASA told me that the moon was a different distance away, I would verify that number for myself by using parallax.
Okay, so how did you derive the distance to the lights in the sky? So maybe I should rephrase that slightly by just asking what variables did you use to derive the distance to the lights in the sky?
I don't know how far away the lights in the sky are. All I know is that they are demonstrably behind the moon because the moon can obstruct the light from those lights. And I know that they are sufficiently far away because the stars do not demonstrate any detectable parallax for any two observers on Earth simultaneously. If an object demonstrates no parallax for two observers a great distance apart, then that means that object is very, 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 very far away. The moon demonstrates measurable parallax, as my video has shown. The stars do not. This gives us reason to believe that the stars are further away than the moon.
Okay, so a question. This is obviously to yourself. Why did you even bother question mark? However, the question is, in order of this fantasy space to exist, 95% of the space must be invisible. What is the point then if he have only 5% knowledge and 95% guessing?
I guess my response to that would be actually to use a flat earther response. Flat earthers, a number of them, I know this because I've seen a number of their videos, they'll say that science tells us that the Earth is a globe and that we've explored all of it, and so there's nothing new to see here. And flat earthers will say instead, well, no, the Earth is flat and it might go on forever, so there's so much more for us to learn, so much more for us to detect and discover. Well, if it turns out we only know 5%, we can only detect 5% of matter in the universe, I think that's the reference that's being made, that like I think that's the reference being made. If we only know 5% about the universe, that's great. That means there's still so much more for us to learn. And I think it's an incredibly childish attitude to say, well, what's the point? Wouldn't you rather learn more? Wouldn't you rather strive to understand the universe better?
Okay, so a question from Chris Cruel. Does the assumption of a sphere or a flat Earth disqualify any of your measurements?
No, as I made it clear in my video multiple times, parallax does not assume the shape of the surface that the observations are made from. Parallax works exactly the same whether you're on a sphere or an egg or a parabola or a hyperbola or a flat plane or, I don't know, a cube.
Okay, so a rhetorical question from Oxbow Spirit. How many 20-foot tape measures to reach an intangible object?
I don't know.
So from Sleeping Warrior, the original question, so he asked this at the start, and obviously you brought him into the presentation. So the question is, as a ratio, Sirius must parallax with Betelgeuse. So anything like 1 to 250, 1.250, but we do not observe this. Ask Jeff to confirm the ratio, then explain why there isn't any parallax.
Okay, so because he asked that at the beginning of the presentation, I'm not sure he stayed for the presentation. I'm not sure he saw my appendix where I addressed this matter specifically, so I'll summarize it again. Sirius, being about 8.5 light years away, has a parallax of less than 1 arc second. It's about 1/3 of an arc second. Betelgeuse, which is about 642.5 light years away, has a parallax of 0.005 arc seconds. So it's true that Sirius's parallax is 76 times as much as Betelgeuse's. However, both measurements of parallax are less than 1 arc second, which is 1/3600th of a degree. And that amount of movement is undetectable to the human eye. It would be the same attempt as looking at an object 8.5 miles away and an object 642.5 miles away and moving your head 1 inch and expecting to detect any change in their locations. So that is my response to Sleeping Warrior.
Okay, so from Constance Bruns, how does the gentleman provide that measuring distances of earthbound objects is the same as measuring distances between or two celestial objects?
Is there a reason that the measurement of terrestrial objects, is there a reason that the method of parallax for measuring the distance to a terrestrial object should suddenly not work for an object simply because it is not on the surface of the Earth? I would say no such reason has been presented yet. No such evidence to disqualify parallax has been presented. On the contrary, you can use parallax to measure things in the sky. You can use parallax to measure the distance to a plane. You can use parallax to measure the distance to the ISS, as Res Rhetoric and Astronomy Live have done. You can use parallax to measure the distance to the moon. You can use parallax to measure the distance to the planets. And you can use parallax to measure the distance to the stars if you have technology accurate enough.
Okay, so what are all the variables needed to measure the distance to the moon?
The variables you need 2 observations taken simultaneously, and this is important because if the moon does move, you want your 2 observations to happen at the exact same moment in time. So you need 2 observations taken simultaneously. You need to know the distance between those 2 observers, and you need to know the pixel to angle ratio of the images that you take. Those are all the variables you need, as demonstrated in my presentation today, to determine the distance to the moon or to any other object whose distance you attempt to measure via parallax.
Wouldn't you need to know the size of the object, like in this case the moon, as well?
Nope, you don't need to know the size of the object. The size of the object doesn't enter into the equation at all. The object could be a single point of light. It doesn't need to have any measurable size at all. However, once you've determined the distance to the object using parallax, you can determine the object's actual size by taking its apparent or angular size and the known distance.
Okay, so did both Einstein and George Ellis state in their own words whether Earth is moving around the universe or vice versa? All motions are accounted for and indistinguishable.
I have no idea if both of them said that or not. I would suggest he look up on Google or something. I don't know everything.
Okay, so from Count, why can we see through the moon sometimes?
I've never seen through the moon, so if you can provide me video evidence of somebody being able to see through the moon, in fact, if you could send me video evidence of 2 people in 2 different locations simultaneously being able to see through the moon, that would be astonishing, and that I would look into. But until you do that, the only evidence I've ever seen of people claiming to be able to see through the moon are unfindable sources from documents from a Royal Astronomy paper from the 17 or 1800s. Never actually seen the actual document. I've only ever seen it cited. I've never seen like a facsimile of the actual document. Still images I've seen, those still images are too hard to fake. Still images can also suffer from dead or hot pixels in a camera that make it appear that you can see a star where there is no star. So yeah, I've never seen any credible evidence that you can actually see through the moon. Every time I've attempted to see through the moon, I can't.
Okay, so a follow-up question from Sleeping Warrior. So ask Jeff to show the relative distances as a ratio of Sirius over Betelgeuse, then demonstrate how the expected parallax is consistent.
Okay, the ratio is 642.5 over 8.6, and that ratio is about 76 to 1. So as I admitted in my presentation, Sirius has a parallax of 76 times Betelgeuse's because it's about 76 times closer. But both of these parallaxes are too small for the human eye to detect. It really comes down to the fact that, yes, 0.379 is about 76 times 0.005, but these are arc seconds. These aren't degrees. So these 2 numbers are virtually impossible for the human eye to detect.
Okay, so we have a question from Pete Shea. Now he asks, ask him to how it was decided that Betelgeuse is 650 light years away.
Well, I would guess a number of techniques were used. One technique would be, surprise, surprise, parallax. This assumes that telescopes were being used that were able to detect the minute shift. Another possible way to determine the distance would be if you can analyze the spectrograph of light from Betelgeuse, you can know the sort of chemical composition of the star, and you can use its apparent brightness and its apparent size in the sky. I don't know for a fact. I would probably want to research that question more fully before I provide an answer for him. I just want to thank Pete Shea so much, though, for not asking one of his infamous questions. So I don't know for sure how Betelgeuse's distance was determined. All I can say is that I suspect parallax was part of the method.
Why didn't you factor in R for your baseline angle, or do you assume a flat plane? What about the Earth sphere baseline?
All right, as my presentation has mentioned multiple times, and as I have now mentioned multiple times, parallax doesn't care about the shape of the surface that you're taking your observations from. So it doesn't matter what size or shape the Earth is. I will say, however, that if the Earth is spherical, then my baseline was too long. The baseline that I used was the distance across the surface of the Earth from Trenton to Miami, and that distance is about 1,046 miles. But the baseline is supposed to be a perfectly straight line, and if the Earth is a sphere, and that 1,046 miles is the distance across the surface of the sphere, then that distance is not straight. That distance is an arc. What I should do is compute the chord length, the actual straight line length between Miami and New Jersey, in order to get a more accurate baseline. Perhaps if I'd done that, my calculated value would have been closer to the reported value from Stellarium. But in conclusion, I did not assume R, I did not assume the shape of the Earth. I simply took 2 points that I believe to be 1,046 miles apart as my baseline.
Okay, so question from Right the Hand. How do we know the stars and the moon are different distances away?
All right, so I mentioned that in my presentation. How do we know? How can we be sure that the stars are farther than the moon? One way is because the moon, even the non-illuminated portion of the moon, can block the stars from view. And this would seem to indicate that the moon is in front of, the moon is closer than the stars. How can we be sure that the stars are very far away? The fact that the stars do not exhibit any detectable parallax from any two locations on Earth, whereas the moon very clearly does. So that is how we can be reasonably sure that the stars are further away than the moon.
So I have a question from Oxbow Spirit who says, is the sun an intangible object?
I don't think it's intangible, but I don't think that I could touch it. I think if I were to attempt to touch it, I would be vaporized. I believe the sun is made up of physical matter. Whether that counts as tangible is up to Oxbow. But I do not believe the sun to be a metaphysical object. I believe it is a physical object made out of matter.
Okay, so from Dilly Gill. Question, could other mathematical models work with sizes and distance?
I've heard Jaren from Jeranism often say, they tell you that the moon is 250,000 miles away and 2,000 miles wide. But the moon could just as easily be 1,000,000 miles away and 8 million miles wide. The problem is that even though those two objects would have the same angular size, they would have significantly different parallax. Parallax is a way of determining actual distance to the object, not relative distance, not a ratio of distance. What this means is, if the moon were only 3,000 miles away from Earth, it would demonstrate so much more parallax than the moon actually does. I could create a video and post it to my channel, in a couple days, showing what the parallax of a moon only 3,000 miles from Earth would be, and it would clearly demonstrate that the moon can't only be 3,000 miles away based on the observations that can be made from it on Earth. Another reason why the moon can't possibly be as close as 3,000 miles away is that if the moon were that close, then an observer in New York City and an observer in Los Angeles would see very different surfaces of the moon. They would see different faces of the moon from their locations. The fact that pretty much everybody on Earth sees almost exactly the same part of the moon's surface simultaneously, that is also evidence that the moon is very far away.
Could I just ask, is that an assumption that the moon is a sphere, though?
The spherical shape of the moon is pretty well established by the fact that it appears circular no matter where you look at it from. If the moon were a flat disk, the moon would look more elliptical the less directly you're looking at it. The spherical shape of the moon, I'm actually struggling to find reasons to doubt the spherical shape of the moon. If you could recommend a couple reasons why, then I might try to rebut them.
Well, I think it's following on from the line of questioning before about intangible objects. So, we talk about, the questions in the chat are basically around the stars could be intangible, the moon could be intangible, the sun could be intangible. I mean, that's a follow-on question from them, essentially.
Okay. Whether or not they're tangible is irrelevant to the question of parallax, because all parallax is doing is determining the distance to something you can see. So even if the moon is an intangible pixie that magically produces light, the fact remains that magically produced light appears to be 240,000 miles from Earth, pretty much no matter where on Earth you try to measure it from. And the reason why parallax comes up with this number and not a number of 3,000 is that it doesn't assume the shape of the Earth. When people get a distance of 3,000 miles to the moon, they're assuming the shape of the Earth in order to get those calculations.
An interesting question from Cowabunga Joe. Can you measure parallax of a rainbow?
I think you could. Rainbows are a good example of a more or less intangible object. Rainbows are the projection of light from the sun through water droplets. And that light is coming to you from a certain location. And you probably know that, like, if you see a rainbow and you move around, that rainbow appears to be moving at a different rate than the rest of the foreground. So you could measure the parallax of a rainbow, and what that would tell you, I'm pretty sure, is the distance to the particular water droplets that are causing the refraction effect. I think that's what you'd be measuring, the distance to the water droplets that are rendering the rainbow to your eyes.
Okay, so we have a question here from Jason McCormack. What if the moon was 7 miles wide and all objects smaller to reflect this? Would the math still work?
As I mentioned before, if the moon were 7 miles wide, it would certainly not appear to be half a degree in the sky, because parallax tells us that the moon is over 200,000 miles away. So I'm pretty sure we wouldn't even be able to see the moon if it were only 7 miles wide. And once you scale down those numbers, like Jeranism can do, like you scale the numbers up, you scale the numbers down, the angular size stays the same, but none of the other observations would. So I'm sorry to burst Jason McCormick's bubble, but no, you can't simply scale the moon down to 7 miles wide and have all of these calculations still work.
Okay, so question from Doc Michael. Any idea of why the Egyptians use a flat disk representation of the sun, and why don't they use a spherical representation?
Were they creating 3D art, or were they etching on a two-dimensional surface? I don't know of any three-dimensional art really by the Egyptians, except for like the Sphinx, and I guess you could call the pyramids and whatnot. But I don't know of any three-dimensional depiction of celestial objects. So it's the same reason that if I were to draw you a picture of the sun would look like a circle, because I can't really draw a sphere, because a sphere is 3 dimensions and the surface I'm drawing on is only 2. But I mean, when you look at the sun, when you look at the moon, they appear to be circles because you can't really perceive their depth. Whereas if you were holding a lacrosse ball or a golf ball in your hand, you'd be able to tell that it was spherical because it's close enough that you can perceive the depth of the edges versus the closest part.
Okay, question from LBB Store. What is your definition of intangible? Please explain how the sun meets the criteria of a tangible object if you assume it to be so.
So my definition of intangible, I guess you could say intangible literally means cannot be touched. Cannot be touched might be too vague, though, because like I said, if the sun is a ball of burning plasma, I can't touch it. I can't get close enough to it to touch. But I would say that intangible probably means not made up of a physical substance, not made up of matter. And I don't have any evidence to suggest that the moon is not, or that the sun is not made up of matter. I don't have any evidence that the moon is not made up of matter. I'm curious if there's any evidence to suggest things that we can see are intangible apart from light itself, because I'm pretty sure photons are not believed to have any mass. They're not made out of matter. So photons themselves would be intangible. But yeah, so I don't have any reason to believe that the sun or the moon is intangible. Simply because I can't touch it, that doesn't mean that it's not made up of physical matter.
Okay, so I'm going to ask probably another 3 or 4 questions. Could you explain, if you know, how they actually determine the distance to the sun?
So there are a number of ways. I think the way that's most commonly talked about is by using the transit of Venus. And the transit of Venus required a rather fortunate assumption that Venus was about the same size as Earth. That assumption was made for non-reasonable reasons. It was an illogical assumption to make. As it turns out, Venus is about 95% of the Earth's size, so the assumption was almost correct, but it was an assumption that was made, assuming Venus was the same size as Earth.
That was rather lucky.
Yes. They essentially did a parallax measurement during a transit of Venus across the face of the sun, and they again assumed Venus had the same size as the Earth. Later technology enabled us to bounce lasers, radar ranging, the way that a speed gun works, the same way a police officer can figure out how fast you're going. That technology allows us to bounce light off of the moon or off of Venus and to get a rather accurate distance to that object. So once you actually know how far Venus is by using radar ranging, you can then determine what its actual size is because you know its distance now and you know its angular size. And as it turns out, Venus is about 95% the size of the Earth. And then using that to correct the calculations that were done during the transit of Venus, that way you can determine the distance to the Sun. Now, it might not have been a transit of Venus. It might have actually been like Venus at the greatest elongation. But it all pretty much comes down to the same thing. But yeah, once we knew the distance to the Sun, we were then able to give actual, not simply relative distances to all the other planets. Like, we knew that Jupiter was about 5 times further away from the Sun than the Earth was, but we didn't know the Earth-Sun distance. Once we were able to come up with a value for the Earth-Sun distance of about 93 million miles, then we were able to come up with actual distances to the other planets. And that's how we can know about how big they are, even if we've never been to that planet.
Okay, so essentially all the planets' distances were derived from the original assumption regarding Venus's size, yeah?
No, I don't think so. I think Johannes Kepler, I think this was before any attempts. Yeah, Johannes Kepler came up with his 3 laws of planetary motion. And one of them had to do with the amount of time it takes a planet to go around the Sun is related to the distance of that planet from the Sun in such a way that the square of the period of the planet, in other words, the square of the number of Earth years that a planet takes to go around the Sun, is equal to the cube of that planet's distance from the Sun relative to the Earth. So, for example, if you were to watch the planet Jupiter over the course of a little more than a year, you would find out that Jupiter takes about 12 times longer to go around the Sun than the Earth does. In other words, the Earth goes around the Sun in a year, and Jupiter has only gone a 12th of its orbit around the Sun. Using Kepler's laws of planetary motion, 12 cubed is 144, 12 squared is 144, and the cube root of 144 is about 5.2. And that means that according to Kepler's laws of planetary motion, Jupiter is about 5.2 times the distance. Jupiter is about 5.2 times further away from the Sun than the Earth is. But that's only a relative value. You need to know how far it is from the Earth to the Sun to know the actual distance to Jupiter. But it was Kepler who came up with the relative distances to the planets.
Okay. How did our galaxy end up a flat disk?
I have no idea. I mean, some galaxies don't appear to be flat disks. Some of them appear to be more bulbous. If I had to guess, I would say that our galaxy is kind of a flat disk, maybe because it's older and it's been spinning for so long that the flattening process has had an effect. But I have absolutely no idea. That's just a complete guess for me.
Okay, so on parallax triangulation, is the radius of Earth factored into the equation as shown in diagrams with lines drawn through the Earth? If so, prove R, please. R being radius.
Right. So, you may see some diagrams online that assume that the Earth is spherical and measure parallax that way. The technique that I have used today does not assume the Earth is spherical. I don't need to attempt to prove or assume R at all. However, once you have computed the parallax of the Moon, it tells you, for example, that the Moon is almost 250,000 miles away. And the fact that the Moon is 250,000 miles away means that it's about 2,000 miles wide. And that means that if we see the Moon rise and set on Earth, that would require an awful lot of refraction of light if the Earth were to be flat. So that is why you don't need to assume R, you don't need to assume the shape of the Earth to do parallax, but once you've done parallax on the Moon, and then once you've observed the Moon appearing to set and to rise, that leads you towards the conclusion that the Earth can't be flat, that the Earth has to be spherical. you can determine the radius of the spherical Earth by other means. You can't determine the radius of the Earth by doing parallax measurements on the moon.
Okay, a question from Lumberjack. Why can't you just use parallax to get the sun's distance? You just did it to the moon.
I never said that you couldn't use parallax to determine the sun's distance. The problem with using parallax on the sun, however, is that we can't see the background behind the sun when the sun is up. We don't have a background to line up between our two images. The only time that one could conceivably do that is during a total solar eclipse. During a total solar eclipse, when the brightest part of the sun is obscured by the moon, you can see other stars in the sky. And therefore, if you were to take two observers who were both in the totality shadow during a total solar eclipse, if they took photos of the sun against the background of the stars simultaneously, then you could compute the parallax of the sun. You would not get the parallax of the sun to be the same as the parallax of the moon, because the moon is closer and smaller. Just because the sun and the moon appear to be the same size doesn't mean that they're actually the same size and distance. If you do that parallax measurement of the sun, you'll get a parallax measurement that is somewhere in the vicinity of 100 million miles away. I can do a video about that if people would really like.
I'm sure they would. Right, so this is Realistically Speaking. That's his channel name. And final question I'm going to take from Pete Shea. What would be the implication if the Earth was proven not to move?
That is a good question. That's outside of the sphere Earth, flat Earth debate. Let's say the Earth didn't move. That doesn't change anything about parallax measurements. So first of all, that wouldn't change the distance to the moon. It wouldn't change the distance to the sun or to the stars. All it would mean is that the Earth were stationary and everything else was moving. The problem that introduces is that the moon appears to go, from our perspective, the moon appears to go around the Earth in about like 25 hours. If the moon were 250,000 miles away and it goes around the Earth in 25 hours, we can determine the speed that the moon would have to be traveling. Furthermore, if we can determine that there's a star 4.22 light years away, like Proxima Centauri, and if that star 4.22 light years away is going around the Earth in 23 hours and 56 minutes, we can determine how fast that star is moving. What we'll end up finding is that things in the universe would have to be traveling incredibly fast, much faster than the speed of light, in order to be making an orbit around the Earth every 24 hours. The fact is that we've measured the speed of light, and we've not been able to measure anything ever going faster than that speed. So for us to have found that these stars are going multiple times the speed of light to go around a stationary Earth, that would seem to imply that it's the Earth that is spinning and not everything else around the Earth. If we found out for sure that the Earth were not rotating, that would be astonishing. That would probably require a new look at whether the speed of light really is the upper limit of velocity.
Okay, I was going to make that the last question, but if you're happy to answer just two more.
Yeah, no problem.
Right, okay, so from Manny Pinocchio, ask him why do total solar eclipses only occur during a new moon?
Okay, so a total solar eclipse can only occur during the new moon phase, because in order for the sun to be eclipsed by the moon, the sun, the moon, and the Earth have to be perfectly lined up. And the only time that perfect alignment can happen is when the moon is in that physical line, that physical space directly between the Earth and the sun. and that always happens during the new moon phase. Like if you were to draw it out on a diagram, the only time the moon can block the light of the sun is during the new moon phase. Now, we don't get a total solar eclipse. We don't get any solar eclipse every new moon because the moon is not always perfectly vertically lined up with the sun. Sometimes the moon is too low in the sky or too high in the sky to exactly block out the sun. The moon's orbit is tilted about 5.1 degrees from the ecliptic, and this is why it's not every new moon gives us a solar eclipse. And the same can be said for lunar eclipses. Total lunar eclipses only happen during the full moon phase, and the moon has to be just perfectly lined up to go completely within the Earth's shadow. We can get a partial solar eclipse, and we can get a partial lunar eclipse when that alignment is not perfect.
Okay, final question from Gleam. Parallax will only give you an angle and ratio result until you insert a mileage/distance figure. Could the distance be wrong as the ratios will remain the same?
So parallax gives you an angle, and the distance that you're measuring that you don't know, that's what you're trying to figure out. The distance that you do know is the distance between the two observers. So as long as you know the distance between the two observers, you will know the distance to the object. So I don't really know how to give Gleam the sort of answer he's looking for, because basically what it comes down to is once you have a specific baseline for that parallax angle, it tells you exactly what the distance to the object is.
Okay, so if we do happen to get a rebuttal video against this presentation that you've done, would you be happy to enter into a debate, a formalized debate with someone over that?
I would be very happy to enter a polite, civil debate about this topic, yes.
Excellent. Right, I'm going to give you the floor for the next, up to 5 minutes if you want. If you want to plug your channel or anything else you want to talk about, I'll leave it up to you, and when we're finished we'll round up. And by the way, thank you everybody for stopping by. I have another show later on tonight as well, so stay tuned for that. So over to you, realistically speaking.
All right. So first of all, thank you, Ranty, for this platform. I'm glad that you're being civil and polite. I've had some conversations with a flat earther named Uber Flat Earth on my YouTube channel, and our conversations were always incredibly polite and civil. And that's how I prefer this conversation to be. I also thank you for putting up with me. I know I had to delay this a couple weeks. My Friday schedule ends up not being as free as I want it to be, but today it worked out. I've presented pretty much all I want to present about parallax here. I just have a couple other comments related to conversations I've had with Sleeping Warrior in the past. The first is, for a long time, he's disagreed with me about the ability for a person to know which direction north and south are. He always brings magnetic declination or inclination into the situation. And I've told him on several occasions that you can determine north and south simply by using the sun or the moon. You don't need a compass at all. You don't need magnets at all. And that once you know what north and south are, you know where east and west are. And so a good proof of whether the Earth is spherical or not would be to go to the equator of the Earth, determine which way east or west is, and then go east or west in a straight line. And make sure you're going in a straight line. If you can continue on the equator in a straight line without ever having to turn left or right, then that means you're on a sphere. Because on every flat Earth map of the Earth, the equator is a circle, not a straight line. He also seems to have problems with triangles in general. I'm the one who was behind that infamous 1 by 1 by 1 triangle. What are the angles? And it took him a long time to get that it was an equilateral triangle with 60-degree angles. He questioned whether a 3-4-5 triangle was a right-angled triangle. I'm more than happy to explain the math and the geometry and the trigonometry that's required to do these sorts of measurements and calculations. There's too much lack of education in the flat Earth debate. And, so I think people should spend a little more time in math and geometry textbooks and actually do the math before they try to make claims that assume the math has already been done. That's all I have to say. Thank you again, Ranty.
No worries, no worries. Well, thanks very much. We nearly got to 100 people watching. We're on 99, so didn't quite break the 100, but it was close enough. Thanks, guys, for stopping by. Sorry, go on.
I was going to say, I guess that's because I didn't open the YouTube video. Sorry.
Oh, we do have 100 watching now. Well, excellent. Right, okay. So, yeah, we'll have another show shortly. I was hoping to get it done around about 8 o'clock, but it looks like it will be 9 o'clock now. So that will be 9 p.m. BST. So literally about an hour and a half from now. And this time we'll have a flat earther on, and he will be rebutting, wait for this, Bob the Science Guy. So Bob the Science Guy did a presentation last week, and we have a rebuttal from a flat earther who wishes to challenge the presentation that he put together. So stay tuned for that, and hopefully see all you guys back in about 90 minutes. Realistically speaking, thank you very much for showing up, and I enjoyed the presentation. You answered all the questions. Thank you very much.
You're welcome.
Right, I'll call you back in about 2 minutes, and in the meantime, we'll do the introduction, and I'll see you all in the next one.